Welcome back, students. This is the last lecture. We'll talk about molecular symmetry and group theory. And our goal for this lecture is to apply group theory to determine the vibrational modes. So what we're going to want to do today is figure out, one, how do we apply our symmetry and group theory to vibrational modes? And then we're going to be able to determine the representations of vibrational modes. And of course, we'll use our C2V point group as we've been using as an example. And then once we know which representations our modes belong to, we'll actually be able to determine if they are IR or Raman active. So this is how we can figure out if our modes are symmetric or not based on the representation that they belong to. And then this will tell us if we will expect to see them using IR or Raman spectroscopies. So we talked a little bit about vibrations. We've done a couple labs about this. And our example, like it has been for the whole chapter, is going to be water. And you'll recognize the similarities between water and SO2 like we did in our lab. So both water and SO2 are bent molecules, and they're triatomic molecules. And hopefully at this point, we're pretty comfortable figuring out how many vibrational modes a molecule will have. So atoms have 3 degrees of freedom. They can move in 3 dimensions. And so molecules have 3 degrees of freedom per atom. And you can see that represented here. Now, our water molecule, in addition to these 3 vibrational degrees of freedom that are shown, it has 3 translational degrees of freedom and 3 rotational degrees of freedom. So those translational and rotational degrees of freedom are available to all nonlinear molecules. And the remaining 3n degrees of freedom they have, which is now 3n minus 6, because we've taken away 3 for translation, 3 for rotation, are left for the vibrational degrees of freedom. Now, linear molecules only have 2 rotational degrees of freedom because if they rotate along the bond axis there, that doesn't change anything. And so they have 3n minus 5 vibrational degrees of freedom. We can best describe the vibrations of polyatomic molecules by using vibrational modes. So if I were to take this water molecule here and just stretch this OH bond would also change in relation to that, which makes it pretty hard to describe the vibrations of bonds. We can't just describe what's happening between these 2 atoms. So in order to do this, we transform to normal coordinates. So we talk about these normal vibrational modes. And we talk about the normal modes for the following reason. So when we're talking about the normal vibrational modes, the center of mass does not change as a function of vibration. So in all 3 of these different motions, the center of mass stays, approximately here in the molecule. It doesn't change. That's helpful for describing these. Also, all the bonds or the atoms that are vibrating reach their maximum and minimum amplitude at the same time. So they're moving in concert. All of these modes are also independent of each other, at least in the harmonic approximation of the bonds. And one mode can't transfer energy to another mode. So if we excite this mode here, that's all that we see. We don't see any other changes. So we can excite this one and this one and this one. Of course, we can excite them in combinations. And the last thing we can say is that all of these vibrational motions, so any complex vibrational motion this water molecule will have, can be described by different extensions of these 3 normal modes of vibration. So what we want to do with this is apply our symmetry operations to this. So how do we do this? We're going to look at the C2 rotation for the water molecule and try to figure out what effect that would have on vibration. Now, the way we're going to do that is maybe not obvious. So one, how can we talk about this motion and associate symmetry with that? What we're going to do is assign a coordinate system to basically the center of every atom. So we're going to go over here and apply a different coordinate system on all of these atoms. And so the kind of notation here can vary. But what we're doing is we're setting up this hydrogen as atom 1, this oxygen as atom 2, and this hydrogen as atom 3. And each of these has a set of vectors that's associated with it: x1, y1, z1, x2, y2, z2, x3, y3, z3. And we have seen this before. We've done a pretty similar thing trying to figure out what would happen to a point when we transform it. So now what we're going to try to do is figure out what happens to this whole molecule when we transform it. So we're going to start with the C2 rotation. If we take this molecule and we rotate it 180 degrees around this C2 rotation axis, what happens to all of our coordinates? Well, you'll note a couple of things. So first, what happens to our oxygen atom? Well, our oxygen atom here, the Z2 is totally unchanged, it's lying totally in plane with this axis. So that is unchanged. Now, the X2 would be swung around 180 degrees and become negative X2. The Y2 would also be swung around 180 degrees and become negative Y2. So the way that this transformation affects the oxygen atom coordinates is that X goes to negative X2, Y2 goes to negative Y2, and Z2 goes to Z2. The hydrogen atoms are actually different. So what happens to the hydrogen atoms? Well, if we take this one and swing it around 180 degrees, we find that not only does the X1 change from pointing in this direction out of the screen to pointing into the screen, but it's also now where X3 used to be. So X1 becomes negative X3. In the same way, Y1 becomes negative Y3, and Z1 becomes Z3. The sign doesn't change for those Z dimensions. And of course, the same is true for our X3 components. So we're going to do the exact same thing that we've done before. We're going to take a vector. In this case, it's a 9-dimensional vector with each of these coordinate systems and say, what happens to this vector when we do a C2 transformation? And what we find is that, like we just talked about, our vector x1, y1, z1, x2, y2, z2, x3, y3, z3 becomes a new vector, minus x3, minus y3, z3, minus x2, minus y2, z2, minus x1, minus y1, z1. Now, what do we do with that? Well, we do the same thing that we did before. So now we want to construct a multiplication matrix that will allow us to convert this into this. And it's still pretty easy for the C2V point group because all we're doing is turning x1 into x3, y1 into y3, and so forth. We don't have any combinations of these things. So in the homework, you'll go through constructing these. The answers will be here for you to reference on the slides and also in the book, I think. And you can look at these and figure out what we're trying to do here. And we'll go through this one for C2. And we'll see the other ones on the next slide. So for C2, we come up with the following matrix. So we need to multiply x1, which goes into this first column, by something to return at negative x3. And so each of these columns in this matrix is a different dimension. So we have x1, y1, z1, x2, y2, z2, x3, y3, z3. So to turn negative x1 into negative x3, we have to have a negative 1 in the x3 slot. And the same is true for y3. So to turn y1 into y3, we need a negative 1 in the y3 slot. And to turn z1 into z3, we need a 1 in the z3 slot. And so we just construct this matrix in this way. And so we have this matrix that's mostly zeros with 9 entries that when we multiply our matrix here by this C2 matrix, we will turn this vector into this new vector. And we can come up with other matrices for the other symmetry operations. So here we have a sigma v prime, and of course the identity operator is just ones down the diagonal. Now, it turns out that we can do something special with these representations. So if we think about it, we talked last time about reducible and irreducible representations. Are these 9 by 9 matrices irreducible? And the answer is, of course, no, they have to be reducible. Why do they have to be reducible? These are representations of the C2V point group, and we know that the C2V point group can be reduced down to 1-dimensional representations. So if we have a 9-dimensional representation, something is going on here. We need to be able to reduce this further. Now, how do we go about doing this? And of course, when we try to work with the math here, we can bring up components from group theory that help us explore these things. So how do we do this? we'll end up with this little representation here. Now, what these representations are the sum of the diagonals of the matrices. So if we go back and sum up the diagonal elements, so strictly what's going on this diagonal element here, we'll see for E, we get 1 plus 1 plus 1 all the way down for a total of 9. And that was the entry in that representation. Now for our sigma V, if we add up all of these, we see we only have a 1, and a -1. So that would give us a representation of 1. And you can do that for the other ones, and you can come up with this here. So we have 9, -1, 1, and 3. And this represents our reducible representation. Now, how do I take this and put it into irreducible representations? It turns out that we have a thing from group theory to do this. So to decompose this, what we need to do is multiply this representation here by each of our irreducible representations in turn, and then divide by the order. And the order is the number of symmetry operations we have. So in this case, it's 4. And when we do that, we'll end up with a single number that talks about how many of these irreducible representations make up this reducible representation. So how do we do this? Let's go through and do it for A1 here. So what we need to do is take A1 and multiply this by this representation here. We're going to take this scalar product, which means we're going to add these all up together. So here we take 9 for E and multiply it by 1. Then we take -1 for C2, multiply that by 1. Take 1 for sigma V, multiply that by 1. And 3 for sigma V prime, multiply that by 1. And if we do that, that gets us 12. And we divide that by the order of the representation, which is 4. There's 4 symmetry operations in the C2V point group. And that gives us 3. So what this means here is that in this reducible representation, there are 3 representations that belong to the A1 representation. And we'll talk about how we use this coming up. So we can do the same thing for the next 3 types of representations, and we get different answers because they have different entries here in the character table. So for A2, we get 1, for B1, we get 2, and for B2, we get 3. So our 9-dimensional representation here has 9 one-dimensional representations that make it up. So what this means is that our C2V molecules, when we're talking about their motion in this way, they have 3 A1 representations, 1 A2 representation, 2 B1 representations, and 3 B2 representations. And since we described the coordinates and how the coordinates are changing for all 3 of our atoms in this molecule, these correspond to the different types of degrees of freedom that atoms in this molecule have. So if we go back here, just look at the picture, we have 9 dimensions described here, which are the 9 dimensions of our degrees of freedom, our 3n degrees of freedom. So if we're talking about these kinds of motions coming from symmetry, these different representations, they should account for all of our degrees of freedom. Now, how do we go about looking at that? Let's think first about translation. Now, when we're talking about translation, what is happening to our molecules? Well, we have 3 translational degrees of freedom, and that corresponds to physical motion, right? Translation in the X dimension, the Y dimension, or the Z dimension. And wouldn't you know it, our character tables tell us what representations the X, Y, and Z dimensions belong to. So the translational motion of this molecule or molecules of the C2V point group are accounted for here in the A1 representation, the B1 representation, and the B2 representation. And we can do the same thing for rotation. So our character table also tells us that rotation in the X, Y, and Z dimensions belong to the B2, B1, and A2 representations. So we know that our 3 translational degrees of freedom are in these 3 representations. Our 3 rotational degrees of freedom are in these representations. So what about vibration? Well, just like when we were calculating how many vibrational modes there are, our vibrational degrees of freedom are basically whatever is left. So our total degrees of freedom here, 3 of them were in the A1 representation, only 1 of those has been spoken for, and there were 3 in the B2 representation, and only 2 of those have been spoken for, whereas the A2 representation and both B1 representations have been accounted for. So our vibrational modes, therefore, then belong in Two of them are in the A1 representation, and one of them is in the B2 representation. And hopefully this is starting to sound familiar to you from our lab using sulfur dioxide, where we saw that we had two type A motions and one type B signal there in the spectrum of sulfur dioxide. So then what do we do? How do we apply these to the molecules? Here we're back looking at these three types of the degrees of freedom for water. Now, which ones of these belong to the A1 representation and which one of them belongs to the B2 representation? And it's pretty obvious kind of the way that they're looking here, we can figure this out. So if we were to take this guy as it is vibrating, as this one moves up and these two move down, what happens if I do a rotation? Well, if I do a rotation, nothing happens. If I reflect it in this mirror plane, nothing happens. If I reflect it in this mirror plane, again, nothing happens. So as I do these types of symmetry operations, nothing is changing about the molecule. Therefore, this belongs to the A1 representation. This can also be said for the symmetric stretch. However, what happens if I do the same thing to these two? Well, if I do the C2 rotation, now everything is reversed. Now this is moving this way, this is moving this way, this is moving this way. So this gives a -1 in the character table. If I reflect across this mirror plane, it also reverses everything. But if I reflect through this plane, it is not reversed. So this guy clearly belongs to the B2 representation. And so putting these things together, we can see that why these different vibrations happen, why these are the normal modes, because they're what's left from the symmetry operations. And then we can also correctly assign these to their point groups. The last thing we want to be able to do is to determine which of these are going to be IR or Raman active. So what tells us if a mode is IR active? Hopefully you remember that the condition was having a non-zero transition dipole moment. It turns out that in order to have a non-zero transition dipole moment, we need the following. We need to have our transition dipole moment here, and remember it's equal to this integral. And what we've done in this case is we've broken up this integral into the normal coordinates. That's all this Q is here. And don't worry too much about this. I'm not going to put this on an exam or the homework or anything. It's just a mathematical way to talk about this. Now, our mu here is constant. And like we saw before, having a constant number out here means it belongs to the A1 representation. And now what can we say about these functions? Well, here our phi naught, our vibrational ground state, is an even function. And if it's an even function, it changes according to x squared, y squared, and z squared. That's where these squares, these are even functions. So that means that this even function belongs to the A1 representation. So we have an even function here. That means it's in the A1 representation. Our transition dipole moment depends on an actual dipole, which is a one dimensionality. So it changes as x, y, or z. It's an odd function. So we have this function that's A1, that's even. This is odd, meaning it belongs to as A1, B1, or B2 representation. So in order to keep the whole thing even and have a non-zero integral, where we're ending up, our excited state must also change as x, y, or z. And that is a general result here, that things, in order for things to be IR active, they have to have an x, y, or z as a basis for their representation. So for us, for the C2V point group, that means that only modes of the A1, B1, or B2 representations are IR active. Now for our C2V point group for water, all of the vibrational modes satisfy this requirement. So we had two A1 modes and one B2 modes. Both of those have a basis as in Z or Y, so they are IR active. We can do a similar thing for Raman. So for Raman spectroscopy, we have to have a change in polarizability of the molecule. And we can do a similar thing. We're not going to go through why this is the case. You just have to trust me on this one. But they have to have the product of any two of these different things in order to be a Raman active. So they have to transform as x squared, y squared, z squared, or xy, xz, or yz, so the product of any two dimensions. And that for the CTV point group, that is all of them. So again, any vibrational mode, in this case, we still only have A1 and B2, but any vibrational mode would be IR active for the C2V point group. And this is, in general, not true. So for the C2V point group, all the modes are IR active and Raman active, but in general, there's different combinations of modes that are IR or Raman active. So I want to end here by looking at the IR spectrum of methane. We talked about this before. We just mentioned that it was weird. So methane has 5 atoms, which means it should have 9 vibrational modes. So 3n is 15, 3n minus 6 is 9. Methane is, of course, nonlinear. So it should have 9 vibrational modes, and yet we only see 2 peaks. So why is this? Well, there must only be 2 vibrational modes that belong to representations that we can resolve with IR. We can look at this, and if you want, you can go figure out what point group methane is. Otherwise, I'll tell you that it's in the TD point group. And the TD point group has the following vibrational representation. So there's vibrational modes, there's 9 of these modes. One of them is A1, one of them is E, and there's 2 T2 modes. Now, this looks like 3 and not 9, but remember that E, we talked about E last time, and these E representations are 2-dimensional, and it turns out the T representations are 3-dimensional. So here we have 6 plus 2 is 8 plus 1 is 9. So we have 9 representations here. We can look at the character table to figure out which ones of these would transform as X, Y, or Z, and those are the ones that would be active in IR. And it turns out that only the T2 representation is IR active. So that means the vibrational modes that belong to the E and A1 representations are symmetric, and they don't change the transition dipole moment, and they are not active under IR. Now, why do we only see 2 peaks? Well, because we have these 2 representations, and these representations are 3-fold degenerate. So what that means is that we do have 6 modes that are IR active, but they're triply degenerate. So we have 2 different modes, each of which is 3-fold degenerate. We can't resolve the differences there, so we only see 2 peaks for the spectrum of methane. And with this, we can see how group theory is useful. It helps us explain certain things like what are the normal modes and which ones of those would be IR or Raman active. Before I go, I want to conclude for the entire chapter here on symmetry. The first point, we're pretty familiar with it by now, hopefully, that molecules are symmetric. You can use the symmetry of these molecules to put them into point groups, and this point groups will give broad characteristics that apply to molecules. The most condensed form of the symmetry information belongs in these character tables, and the character tables come up with representations that talk about ways in which these different things in these different representations in these molecules can have the different types of symmetry. Atomic orbitals belong to specific representations in the character table. This is denoted by things like x, y, z, xz, z squared, and so forth. And we can use representations to figure out, like we talked about today, what the vibrational modes are and which we expect to be IR, Raman active. And we can also use them to figure out which atomic orbitals would combine to make molecular orbitals. And all of this shows us that symmetry is a very useful thing, and it allows us to group molecules together into having similar types of symmetry. We don't have to treat each molecule individually, but we can say, oh, SO2 is in the C2V point group, and I already know how water works. SO2 is going to work in a very, very similar way because it does the same symmetry. The next lecture, we're going to take a bit of a turn and look at the final type of spectroscopy that you're probably familiar with that we haven't covered yet, and that is NMR. And then after that, we're going to go into some computational techniques and see where modern computation has gotten us.